All right. Yeah, just let me know if you can't see the slides okay, but I think they're posted. So in the function-based rapid stream assessment, the physical part of the assessment, which we sometimes call just the rapid stream assessment, I'm going to walk you through metrics 1 through 5, and then Sydney will walk you through metrics 6 through 11. We'll be practicing all these in the field. Metrics 1 through 5 are relatively simple. We're looking at basically four main things. One of them is visual water quality assessment, channel shading, riffle run, and then pool glide cover, and then velocity depth diversity. And you can see those and where they're applicable. So you're looking for water appearance and nutrient enrichment. You're looking at the whole project reach, but you're only looking in your primary channel threads, so your main stem, lowest channel. The reason for that is sometimes those side channels can get a little funky from like groundwater coming in, iron and stuff, and you can get some misleading looks when you look at those. The second one is channel shading, which we're looking at 3 representative locations across our reaches. And you're also try to represent your channel spreads as well. You might have more than 3 representative locations. This metric is also pretty speedy, so adding additional spots is not going to slow you down much. Then we have riffle and run complexity. So you need at least 3 continuous riffle run units, or continuous, it's actually riffle pool sequences is what you're looking at between the pools and the riffles. So you're alternating between, riffle run, pool glide as you go. And we're just mainly looking in the primary channel, but there's an ability to bump your score if you have hover in those secondary channels. And then your last one is velocity depth diversity. That's for perennial streams only. And again, you're looking in that same 3 riffle pool sequence stretch. The first one we're going to talk about is water appearance and nutrient enrichment. This is a very simplified metric based on, I didn't have the citation here, but we borrowed from a couple different places to create this one. One of them was the RBP form, but we made it so it's easier to determine where your scoring is on these. And it also captures the impairments we see in Maryland. So the important thing to know here is you're looking to fall in one of 3 main buckets. Functioning is you don't really have much going on. You might have a little bit of algae or something like that, a little spot of flock here and there, no big deal. But it's limited to less than 20% of the stream area. And then your next category is for, let me do the worst ones first because it makes more sense that way. Not functioning that's saved for like severe pollutants. Like you've got major chemical water quality issues like sewer leaks where you're getting that gray, smelly water, chemical pollution, oil slicks, major nutrient pollution, things where like the whole bottom of the stream is covered in algae or a lot more than 40% of it. Or you just have iron flocculent that's choking everything up. Hopefully it clears up over time. Are a couple examples. And then, yes, I already talked about the other items. You might also notice some smells, like chemical smells. Just make sure it's coming from your stream and not from somewhere else. And you all have seen these. If you worked in Central Maryland, you've come across creeks like that. Then we have functioning at risk category, which is somewhere in the middle. That's like 21 to 40% of your stream area is affected, usually by something like turbidity, frequent turbidity, or too much iron flocculant, or too much algae. So that's where that sits, and we'll do that together in the field. Give you some examples of what these look like. This is bad news up here on the left. This is where you have probably a leaking sewer main, and you're starting to see that weird gray water that kind of has a smell to it. On the right here, you have a stream that's covered in iron flock. Hopefully this cooks out eventually, and by year 10 or something, if you did construction and this started boiling up, then it would resolve itself. And then we have, just a little too much algae on the stream bottom on the photo C there. D, we've got, excessive macrophyte growth. And then on the bottom, obviously, you have some problems from excessive turbidity and sediment in the watershed. So those are some items you're looking at for the water appearance and nutrient enrichment metric. Some sources to help you figure out what's going on include the 303D list. It's helpful, but be careful with it because it does extrapolate out a lot. And so if you had like a main stem channel somewhere that was affected by metals or something, it might map the whole watershed upstream, and you might have tributaries that have nothing wrong with them. It's just you have that chemical pollution somewhere downstream, so be careful with that. There's some different, assessment reports out there, land use maps and aerials, and kind of understanding the watershed. And if everything's eroding real bad, you might have a bit of a turbidity problem. And then your site visit's the most important thing. So our second metric, and Sydney talked about this one a little bit earlier, is channel shading. And so we are looking at how much canopy coverage you're getting standing in the center of the stream. Usually, I think Denise is on the side there a little bit, but close enough, I guess. And you're going to use a convex densiometer, and there's some grids on it. I'll show you a photo in a minute. And you're basically looking at that, and you're estimating how much coverage you have overhead. And you just want to find at least 3 representative locations. You can add more. It's pretty fast, so it won't slow you down too much. And yeah, we just want to see what portion of the water surface is shaded by mostly shrub and canopy strata, probably not herbaceous, even though that's in there. So there's going to be things that are, yes.
If we're using a densiometer, are there any seasonal or time of year restrictions on when we can do these studies?
That's a great question. So the seasonality here, ideally you're doing this in the summer. If you're doing it out of season, you can do that, but you're going to have to use your imagination and imagine leaf out. So if you're looking up and you're seeing just the branches, you're going to kind of have to estimate what it would be if it was leafed out, just looking at those live trees.
Okay, so then if you're estimating visually, why is the densiometer part of it?
It was a request by EPA Region 3 to keep the method standardized, and we were trying to provide flexibility for you all so that you could do the assessment multiple times a year. Otherwise, it would be restricted to the summer. So you're still using the densiometer and counting points, just the way you count the points is somewhat different.
Okay, thank you.
Sure. So you have your ranges here, 50 to 75% is in the functioning category, 20 to 50% is in functioning at risk, and then 0 to 20% of the water, being shaded is not functioning. And then multi-channel threads, I forgot to mention that part. You would want to try, if you had any substantial stretch of an extra channel, you might want to get a sample there as well and have more than 3 points. So here's a densiometer. This was used I did this one in April. This is in my backyard.
For the multiple channels, would you do representatives on each channel, or you just kind of do the main stem and add a point or 2 on the branches?
Yeah, so you'll do the main stem, and then if you have a substantial stretch of multi-thread channel that you feel like covers the typical condition of channel shading, you'd want to get a point there as well, and maybe a couple of them. It's going to be, you have some flexibility there in terms of best professional judgment of where to take all those points, but they just need to be representative. You're just trying to tell the story. So for this one, we have this densiometer from, this is just my backyard here. You're, level it out, and you got that bubble there. I'll help you do that. And you're counting points. So each corner, and I hope you can see my cursor, each of those corners is a point, and you're determining whether or not you have blue sky or gray sky, probably tomorrow, or you're seeing vegetation. So I'm going to count the points that we don't have coverage here. So we've got maybe 1, 2, can't tell what's going on up there because it's kind of curved. Maybe 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to say I got 12 points without coverage. So 12 times 1.04 is, I can't do this in my head today, we're going to say 13% or something. Does that sound about right? Without canopy coverage. So our canopy coverage in my backyard is about 87%. And now you know why I don't have a garden. So that's how we determine our canopy cover. So you do that, go a few different points that are representative, or if you want to capture the span of it, you're trying to get, okay, one part of it's mostly cleared, one part of it's mostly forested, and you're just trying to get to an average kind of condition. Oh, in this case, 7 corners. I guess I must have used a different number for that. Sorry about that. So we have then our metric again. If we had 87%, like I mentioned earlier, you'd be in the functioning range. That's pretty good canopy cover for your stream. So the next set of metrics, and this will, you'll have to bear with me here because you're doing the measurements for 3 metrics at one time. So you get a lot done with this. And you need to be able to go out and flag off your different facet features. Your pool glides is one unit, and your riffle runs are the other. And you remember your riffle, starts at a hill, a crest, and things start flowing downhill, maybe get a little steeper in the run, and they land in a flatter area where the pool is. So that's one feature. Now the pool starts, and you see the bed kind of start to come up in the glide, and then there'll be another crest, and that's where your next riffle pool feature begins. So you're going to flag those out, and they have to be 3. And then again, this is representative section of your reach. So if you had a portion that looks a little bit nicer and a little bit poorer, you might want to straddle the two. And you have, 3 riffles and 3 pools. So there's 6 habitat units you're looking at in your reach that are representative. And we're going to measure the length of each of those features, depth to water surface, whether your velocity is, and you're eyeballing this, there are ways to check it if you want to, fast or slow, so less than a foot per second and greater than a foot per second. And then the length you're seeing, of that length, how much of the length has some type of cover feature within the cross section. It can be anywhere in the cross section, and that foot counts. And then we also look at the metrics for cover diversity as part of your score as well. So we're looking at large wood or fallen trees, boulder or cobble voids. And those are the voids have to be large enough for a darter to fit in, at least, so like an inch in diameter and have a little bit of depth to it. Flat boulder cover, the type of thing you might find a big salamander under. Bedrock overhangs, they just have to have some depth to them, again, about 0.3 of a foot. Dense live roots in contact with base flow. Macrophyte beds, floating vegetation, but not excessive macrophyte beds, hopefully, that are showing nutrient impairment. Micropools, which are in our riffles only, and then gravel spawning beds. I'll talk about those in a minute. It's important to note, I can't remember if I do this on the next slides or not, but the difference between micropools and pools is a distinction that's important for this assessment. So we define, a pool as a concave surface. It's deeper, or a concave, bed surface. It's deeper than the riffle. In a meandering stream, alluvial valley, it's usually in your outside bend or where you're getting convergent scour occurring. And it takes up, because we had to draw a line here, it takes up at least half of your channel width, the wetted width of the channel. Micropools occur in the riffle run features, and they're great, habitat cover, they add diversity, but they're smaller than that. So they're less than half the width of the wetted channel. And they're usually the result of some complexity, if you're doing restoration, that you placed in the channel that helped make a little scour hole there during certain flow events. So we're talking more about these cover features and some photos of them. So we got some, large wood. And these, again, the cover features, we mentioned this earlier, they have to be relatively fixed. So it can't be something that's just moving with every flow event. We're not looking at detritus in this assessment. It's something that's relatively fixed. It doesn't have to stay there till the end of time, but it should be there and be able to survive a few flow events. You're using some professional judgment there on whether you think that's the case or not. Live roots in contact with base flow. This was a stream with poor water quality, but it did have these nice, I think these were red maple roots, those nice fibrous roots, and that's good spawning substrate. Fish and bugs will go hide in there. If you took your dip net in there, you'll find some things. I also showed a picture of gravel spawning nests. Again, these are relatively fixed features, but you get a big flood, it's going to move. But these are really important in streams because even though they're made by usually river chub or creek chub, other fish species utilize them and kind of get a free spot to drop their eggs. And they have this chub guarding the nest for them so they can go off and eat bugs or whatever else they're doing. But you see, species diversity can improve and richness when you have such features present because this supports spawning by additional species, not just the chubs. They usually pop up in glides, but you can find them in other places. So this talks about what we're looking for in metrics 3 through 5 in terms of specific items. So we're looking for covered features present below the water surface. So we're not, if it's above the bank full water surface, we're not looking at it. Or we talked about dense live roots in contact with base flow. If they're hanging up in the air, it doesn't count. If they're hanging up in the air, but just a couple of them are like dangling in the water, that doesn't count either. This is, it has to be fairly dense. Length of riffle with cover features and percentage of riffle run with cover. Length of pool glide features and the percentage with cover features. The number of cover features present in riffle runs. The number of cover features present in pool glides. The number of velocity depth regimes present, and then the ratio of riffle length to pool length, or riffle run to pool glide. I talked about this. I couldn't remember if I added this language or not. The difference between pools, again, has to be at least half the wetted width of the channel. Usually in outside bends, sometimes you can get something in the, somewhere else where you have a tree fall or something like that. And then your micro pools, again, are smaller and a result of usually hydraulic diversity. If you're starting to see those, you probably did a good job in that particular riffle to create some diversity in your design if it was on a restoration. Important thing, micro pools are not a new facet feature, so you don't count that as a new pool glide feature. It's just a cover type within the riffle run. So this is the scoring sheet for your riffle run complexity. You have your percent cover density, so the percentage length of your stream that has a cover feature within that cross section versus the total length. So greater than 70% or so is outstanding. 40 to 70% is pretty good. Then 20 to 40% functioning at risk. 5 to 19 and less than 5% is not good. And then you have your number of cover features, and this is stratified by stream, kind of the type of stream you're in. So sand bed streams, you're just naturally going to have a little bit less cover features because you don't have options for all those rocky features and things are just not going to be there probably. And then other streams, you have up to 5. So the more diversity of cover, the better off you're going to be there. And then we have our pool glide cover, same thing, a little bit lower bar here for the percent cover because you naturally, a lot of times in the glides, you just don't have as much going on unless you have spawning gravels or something like that. And then again, your cover features the same scale as for riffles for the number of them. So it's split in 2, and then you're adding the 2 sides. So if you had 4 and 4, then you have 8 out of 10. And all of our metrics, I don't know if I mentioned this earlier, they score from 0 to 10. The next part here is recording habitat cover in multi-thread features. So if you remember in the Maryland Stream Framework, you do have the option to add additional threads, but they have to have there's certain criteria to them. They have to be perennial, at least a foot wide, and hopefully they have some cover features in them for the purpose. And when you do your assessment in the stream, and hopefully I'm not confusing folks here, that same habitat score you have from the primary stream, you also use that for the secondary channels that you have on the sides. They're not worth as much credit, but they do provide something. So now when you're doing the assessment, this is slightly different. So you can get a bump in your scores for the riffle run cover and the pool glide cover if certain conditions are present here. So first, on your secondary or third channels, does the length of those is at least 20% of your reach length? If it's not, then you ignore this cumulatively too. So you can count them all up and say, you've got a few of them. And if it's more than 20%, then you follow these steps. If it's less than, you ignore it for the sake of the assessment. You can still add it in the Maryland Stream Framework as a unit. You're just not adding points to those two metrics. So hopefully this isn't too confusing, because I know we had to figure out a way to do this, and this was the simplest way we can come up with. We had a few different methods out there, and stuff gets woolly quick with these. So after you figure out whether or not all side channels equal at least 20%, let's say it does, now you're going to visually estimate the percentage of cover in those side channel riffles. And then you're going to visually estimate the percentage of side channels with pool glide habitat. And if you have at least, I think the number, I didn't write it in here, I think it's at least 30% of those, either one, have those features, then you can add 2 points. And I should have put some more text in here. 2 points to your score for riffle run cover if you have 30% cover there. 2 points to pool glide if you have at least 30% cover there. If you have those features, but they don't have those cover types, you can still add 1 point for their existence. And those are important habitat features, because from my experience sampling fishes across the Southeast when I was in grad school and then later doing sampling, you see different things in those off-channel habitats. So they can be very important for young of the year fishes, or just other species we would find in those sometimes that like that condition better than being in the main flow. So do we have any questions on this one? I know it's a little nuanced. All right, moving on. So the last one I have is for this set is velocity depth diversity, metric 5. And what we're looking for is, this is very similar to the RBP, Rapid Bioassessment Protocol habitat forms that EPA created back in the 90s. And we're looking at the percentage, the number of velocity depth regimes. So you have slow, shallow, so less than a foot per second, less than 1.6 feet deep, slow deep, fast shallow, and fast deep. And so the number of units that you have, you end up falling into a different bucket. And then from there, a ratio of percent riffle run to pool glide helps you figure out where you're at within that range. And you have a little bit different ranges and things of what you're looking for in most riffle pool sequences, and then really low gradient sad bed streams that you might see on the coastal plain. A lot of folks ask, why was 1.6 feet considered deep, or 3.2 in the coastal plain? Those are biologically based. So we reached out to the folks that created the original RBP, and that is where they find the best macro invertebrates when they were doing sampling, was in places, streams that at least had those features somewhere that had that depth to them. And we acknowledge that some smaller streams naturally aren't going to have features that are that deep. And that's okay. They just don't provide that function sometimes. They may provide other ones. It's easier to get complete channel shading on a small stream, for example. So it all balances out. But I just wanted to point that out, because you'll see it in the field. We might see a nice stream that doesn't quite meet the depth criteria. That depth criteria is biologically based. And so if it doesn't meet it, it doesn't meet it, and that's okay. So that's all I had for metrics 1 through 5, and I'm going to turn it over to Sydney for metrics 6 through 11.
Yep, give me a second to get set up. Can you guys hear me?
Yep.
Yes.
Hooray! And share. Can you guys see my screen?
Yes.
Hooray! Double hooray. All right. I'm going to talk about metrics R6 through R11. So those are, sorry, getting my laser pointer set up so that I don't just start gesturing and you guys can't see where I'm pointing. Vertical stability, bank height ratio, entrenchment ratio, floodplain soil drainage. B high is the bank erosion hazard index, and then floodplain exclusion. So walking through, kind of stepping back to our overall process for performing the rapid stream assessment in the field. You just finished your habitat sampling, or finished your metrics. So 3, 4, and 5 were from a habitat sampling reach. When we get to metric 6, again, we're going to look at the entire reach. And then for 7 and 8, we're going to measure them at least at the upstream end and the downstream end of the reach. For metric 9, we're going to be looking for a representative location, and then 10 and 11 are both assessed at the reach scale again. And we will step through each of these, starting with vertical stability extent. So for this metric, walk the whole reach looking for vertical stability issues, such as head cuts or high drops over structures. For any structure or drop that you come across, you're going to measure the height of it, and you're going to measure the height as the actual like bed elevation. So in this case, the elevation on the log down to the water surface at the downstream end of it. So the height of this drop, and hopefully you guys can see that laser pointer, is going to be from the log surface to the water surface. And that'll be the height measured at that drop. For this metric, it is applicable to all channels, and we are looking for localized or widespread downward stream adjustments. And in this photo, you can see an obvious head cut where we would measure this drop from the upstream bed down to the downstream water surface. And this one looks like it's, you know, pushing 2 feet, whereas the other one was probably less than 6 inches. Scoring for this metric is stratified by stream slope. So instead of trying to fit all 3 of the scoring criteria, like the narrative criteria on the slide, I provided the first one. So this is for slope or for stream reaches with less than 2% slope. But everything is the same between all of the slope categories except for this text in red. So when your stream slope is less than 2% slope, any drop that is less than half a foot is going to be okay. But when you're in a stream reach that has 2 to 5% slope, the abrupt dropped height for the functioning category is going to increase to 1 foot. And similarly, there are adjustments in the height drops that are acceptable depending on your reach slope. If you are in a reach that is greater than 5% slope, then the drop height is not needed or is not part of the scoring. You're really just looking for regular grade control structures that are provided by tree roots, embedded wood, rock structures, or riffles, just looking for signs of that vertical instability. Whereas something that is not functioning is going to have widespread instability, active head cuts being common, and abrupt drops that are large in size. Excuse me for a second. All right, let's see if I can get my mouse back. All right, as you are walking the reach and looking for head cuts, in the name of efficiency, I'm usually also going to do that whole reach walk and look for bankful indicators. So armed with your regional curve data that is applicable to the physiographic region of your site, or if you have a site-specific regional curve to help you predict the bankful area, you're going to walk the reach looking for geomorphic features that the reach or that the stream has left. So that mark that is left by the frequent enough flows that are forming the shape of your channel. So that data is recorded. Although we do just record like a single value, I am usually printing the regional curve as shown on the previous sheet, at least the area and the width regional curve, so that I have an idea of the range of scatter that is, hang on, I'll go back to the regional slide, the regional curve. because very few points, very few of the streams that are used to make these regional curves are actually on the line. So there is kind of a range of scatter that these regional curves are predicting, whereas the actual value recorded will give you a ballpark value. These steps for bankful identification and verification. The first one is to print out your regional curve that is applicable for your region. Next, you're going to walk the reach looking for bankful indicators and measure the distance between water surface and that bankful feature. When you're first walking a reach, you might see multiple consistent features at different elevations. So it's possible that there's inner berm or terrace features, or just if you don't know what an inner berm feature is, then you might just see like different levels. So as you're walking the reach, you can record the distance between water surface and those indicators and kind of mark them as like, well, this is the low indicator, this is the high indicator, and keep track of what kind of indicators you are observing within your reach. Once you've identified consistent indicators, and again, oh, sorry, so this picture shows a depth rod being used to test the top of bank feature. And so this other depth rod is measuring the distance between that bankful indicator and the water surface elevation. Once you've identified a geomorphic feature, or maybe you've identified multiple geomorphic features and you're not sure which one's bankful, you will then perform a rapid survey of a riffle cross-section so that you can calculate or estimate the bankful cross-sectional area, and then go back to your regional curve to determine which feature you identified is bankful, or determine if the feature you did identify, like that's the one feature you saw, and you're going to test it against the regional curve. So on the field sheet, table 2 is for bankful identification. There is space to record that distance between bankful and water surface, and also a description of the indicator you were looking at. So whether that was a depositional feature, which are my favorite, or if it was maybe the bottom of a scour line or top of bank in some cases. And again, you might identify multiple features. So you might have a low feature, middle feature, high feature. When you get to surveying that rapid cross-section, and you calculate an area, so maybe you have a really consistent feature and you're like, I like it, I think that's bankful, and then you survey the rapid cross-section, and let's say it plots down here where that little purple X is, or now my laser pointer is covering it up. In that case, you have been seduced by the inner berm. That point is below the range of scatter for the reference reaches, the data that have been collected for that physiographic region. So at that point, you want to go back and look if there's a higher feature consistent throughout the reach that you could survey and test that cross-sectional area. Similarly, this plot shows a really high terrace that is plotting above the range of scatter for this particular regional curve. There is space on your field form to collect that rapid cross-section data. So there's 3 columns, not knowing how big your channel is going to be. I tried to give you as many space for as many data points as we can get. So we've got, you're going to stretch a tape from left to right at the bankful, connecting the bankful indicators. You're going to level the tape by measuring from water surface up to the tape on either side of the channel. That assumes that the water surface is level. And you cannot use that method to level the tape. You'll have to get your hand level out to level the tape if the water surface is doing something funky between the left and the right. But stretch the tape, level the tape, and then start taking readings of station and depth. So the depth being from the channel bed up to your tape. And there's a space for notes, so you can indicate thowwag edge of channel. There's also space to provide some calculations. So entrenchment ratio and bank height ratio are metrics that we are going to assess. But also what we're most interested in right now is going to be that cross-sectional area. So you can perform an estimate while you're in the field, like calculate it from the values you collected. Just to note as well, like when you enter data in the worksheet version of this form, it will calculate the cross-sectional area off to the right for you. Give me a second. All right, so assessing metric R10, which is the bank height ratio. I think this should be R7. I apologize. My numbering is off on this slide. So assessing the bank height ratio. The bank height ratio, once you know where bank full is on your reach, for the riffles at the upstream end and the downstream end, you're going to measure the maximum bankful depth. So from bankful down to the deepest part of that channel. You're also going to measure the low bank height. So of the left bank and the right bank, which one is lower of the two, and measure that height. So that is where the water is able to flow out or spread out onto a floodplain. So what is that elevation or depth from the foul wag to the low bank height? And the bank height ratio is the ratio between those two. So low bank height, which for this picture is 6.5 feet, divided by your bankful maximum depth, which is 4 feet, for a bank height ratio of 1.6, which that 1.6 is not functioning compared to reference conditions. So reference condition streams are connected to their floodplains with bank height ratios of 1 or less. Hang on a sec. I apologize. I didn't want to cough into the microphone. All right, so not functioning streams have a bank height ratio of 1.5 to greater than 7. So on the previous slide, the example was 1.6, so that would score a 2, and we would select for the existing condition a score of 2 for this metric. Hang on. There is some extra guidance that I'm not going to go into too much detail, but just to give you the heads up that it is in the user manual here. So in order to be consistent in when a bankful bench counts as low bank height as well, there's additional guidance that has been added to the user manual for the 2024 FBRSA, so that when I go out in the field or when someone else goes out in the field, we are consistently going to make the same decision of whether this is the low bank height or whether this bench is wide enough that that is the low bank height. So it does require knowledge of the valley that is known. So if you have an unconfined alluvial valley where C or E stream types usually sit, if the total width of the channel and the benches is more than, this says 2.2. When I'm out in the field, I'm really looking at like, is it more than 2 times my bankful width? And if it's smaller than that, then the upper bank, the terrace feature, like up higher, is going to be your low bank height. And I don't know if I can do this justice, but when we're out in the field tomorrow, like definitely flag it and we'll talk through it again when we're like looking at a stream reach. I do have an example cross section. So this is from the Boardman River up in Michigan, where there is on one side of the channel a very small, narrow bankful bench. And so in this case, the low bank height, because this bench is so narrow compared to the size, the width of the bankful channel, this where my laser pointer is what is considered the low bank height. So this stream is incised. And I'll pause there and take a drink of water if there are questions. I must have done a good job. Or not paused for long enough. That is also a possibility. So again, we're measuring bank height ratio and entrenchment ratio at the upstream end and the downstream end. If there's a significant difference between the upstream end and the downstream end when we measure it, we're going to take additional measurements. Both of these measurements are always measured at riffles. So our next metric is entrenchment ratio. The entrenchment ratio is the width of the flood-prone area, so flood-prone width, that is measured at a depth that is twice the bankful maximum depth. So again, that bankful maximum depth, so from bankful down to the deepest part of your channel, you're going to increase or go up, move up from that bankful elevation, another bankful maximum depth, and measure the width of your flood prone. And this is one of my favorite measurements to show in the field, especially when I have more than like 4 people and we can like get the tapes going on the rod, because then you can actually like see it in the field. So the entrenchment ratio is that ratio between the flood prone width and the bankful width. So getting at how far floods can spread out on the floodplain once they are above the bankful stage. Scoring for this metric is stratified by valley type. So for unconfined alluvial valleys, again, those are your really wide, flat valleys. In order to get into the functioning range, you need at least 3.7. So that means the width of your flood-prone area is at least 3.7 times your bankful width. And then to get the 10, you actually got to be all the way up at 20 times. These numbers are from reference data published by the U.S. Fish and Wildlife Service in Maryland. Not functioning when you're in that unconfined alluvial valley setting is going to be when your flood-prone width is only 1.4 or close to only 1 times your bankful width. So that just, if your entrenchment ratio is 1, that means you have no floodplain. If you're in a confined alluvial valley or colluvial valleys, the functioning range is between 1.5 to 2.2. And just remember that those colluvial valleys are just naturally much narrower than the unconfined alluvial valleys. Oh, I added a slide. If you are following along on the PDFs, this one did not make it into the PDFs, but I added it. Just this is a figure from the manual just to specifically address valley restoration. So in order to be a jurisdictional stream feature, you do have to have that bed and banks, like identifiable bed and banks. But where you might have multiple smaller channels throughout the floodplain, just so that we are still capturing the width of the floodplain in these systems, you can use the calculated mean depth from the regional curve. So using that regional curve that is applicable to your region, you can measure up 2 times the calculated mean depth from that regional curve and measure your flood prone width there, which in this instance, I mean, if you have a true connected stream wetland complex, it's probably going to go from either terrace to hill slope, or as shown here, from hill slope to hill slope, and measure that width. You do need to be careful that you are using that same denominator and using the same method from your existing condition to your proposed condition. So if your existing condition is incised and you have a bankful width and a bankful max depth, you want to make sure you're not gaming it for more lift in your proposed condition, and that you are using the same values, particularly that denominator. So if you have a measured bankful width for your existing condition, use that same bankful width for normalizing your flood prone width in the proposed condition. And I'll pause there again. Hopefully I said that clearly. Quiet bunch for these presentations after lunch. All right, so final reminder, when you're scoring the bank height ratio and entrenchment ratio metrics, it's going to be an average value, because you are going to at least measure at your upstream end and your downstream end. If those values are drastically different, you'll want to take more measurements at riffles throughout your reach so that you can come up with an average value. You are not just scoring your worst bank height ratio that you can find within your reach. Oh, wait, this one's a little bit more instructional. So this is showing how you measure it at a cross section. So we've got our bankful indicator and have stretched a tape, and then we're going to identify which bank is the low bank feature. So in this case, it's here shown on the left of the slide. And you can either use your hand level or stretch a rod, like a rigid rod, and put a level on it to measure the height between the low bank feature and the foul leg of the channel. And then you'll divide your low bank by your bankful maximum depth. After that, so if you have a rod stretched in the center or standing in the center of the channel, you will identify the height that is twice your bankful maximum depth. So you'll see where the tape crosses is bankful. So the yellow dashed line is the same height as this red line below. And then either using, I'm sorry, I didn't make it to my mute button. Either using a rangefinder or a tape to stretch, identify where in the floodplain that elevation hits ground, and use that to determine your flood prone width. All right, hey, my numbering is back on track. Okay, so those were metrics 7 and 8. And we are going to talk about metric 9 next, floodplain soil drainage. This is one of the 2 metrics that is not always going to be applicable. So first you have to determine whether or not the valley naturally supports, supported, or could support a stream wetland complex. And this metric is to capture the benefits of floodplain soil saturation and the ecological loss when the valley substrates and riparian community are drained. The parameter that it's assessing is hyporheic exchange or groundwater surface water exchange, but just to note, this does focus on lateral exchange and does not quantify vertical exchange. Ooh, this is a matrix. Okay, so I thought this was, so usually there's like narrative criteria and you pick a bucket on the scale of 1 to 10, but there's a couple metrics that we assess that just worked out better to assess using a matrix. So the first measurement you're going to take is going to be from your floodplain surface down to your base flow water surface elevation. I think I noted earlier, and Nick stated in answer to a question, that there are not seasonal requirements to when you go out and do the rapid stream assessment. However, it is important that you go out in the same season when you're doing subsequent assessments. So if you were out there in the winter for the existing condition, you have to go out there in the winter for the proposed and for any monitoring conditions. Same deal with groundwater, because we know there's, or not groundwater, with base flow, because there can be seasonal differences in base flow, but you do have to be consistent in what season you're going out. Also, you cannot go out, excuse me a second. Sorry about that. You cannot go out right after a rain event. You do have to wait a couple days so that you are assessing base flow conditions. So that is one seasonality requirement or trip planning requirement. Like if it has rained, you do need to wait a couple days before you go out and do this assessment. Okay, so the first measurement you're going to take is from your floodplain surface to your base flow water surface elevation. If that elevation is greater than 1.5 feet, you don't need to do anything else to score this metric's existing condition. You just mark a 1, which is the minimum score that this can get, and you can go on with your other assessments. However, if you are less than 1 or less than that 1.5 feet between your floodplain surface and your base flow water surface elevation, then you will also need to determine your soil texture, and it's the soil texture within the root zone or the floodplain soil. So specifically at a depth that is about 1.5 feet below the floodplain surface. And the 1.5 feet, it seems like a magic number. I promise I didn't make it up, but it's based on like typical rooting depths. So how much of your root mass? Usually somewhere between 12 to 24 inches, and we use 18 inches as an average, is where your primary rooting depth of your floodplain vegetation is growing. So we're looking about 1.5 feet below the floodplain surface, and you're going to determine the soil texture. If you have what is called a gravel basal layer, Oh, and I just flopped. I don't have that definition in front of me. But the gravel basal layer is what it sounds like. So it's got gravels in it, it's got sand, sometimes it's got oyster shells if you're out on the coastal plain. But if it's something that has a lot of pore space and a high hydraulic conductivity, then that is going to score better than if you have something that has more clay in it. So you can see if you have a silty clay or a clay soil underlying your floodplain soils, and those are not providing a lot of exchange between that base flow water surface and the groundwater aquifer.
And for the gravel basal layers, you're looking for a layer that has a little bit of depth to it, but it usually formed from either ice age processes and things being left behind, or a lot of times the stream meandering from valley wall to valley wall over the centuries and leaving some of the material behind as it's moving back and forth across the valley. But it should have at least some depth to it. And I think we provide some clarity there in the manual.
Yeah, I can't remember if we say 3 inches or 6 inches. And you are measuring, oh no, wait. No, I won't say that. Yeah, it's not just a thin lens of a gravel, but yeah, it's either 3 or 6 inches, I believe. All right, and then I pulled back the picture from that head cut to show, I mean, to me, upstream, this looks like it might be maybe more of a linear wetland feature, but just where it has incised and there's a head cut working its way upstream. So you are going to measure the depth from the floodplain surface down to the water surface. So if that depth is greater than 1.5 feet, this metric scores a 1. If, let's say, this floodplain surface down to the water surface elevation falls in this bucket, so if it's between 1 and 1.25, then it will depend on the soil texture. So if this soil is a clay loam, and my depth from the floodplain surface to the base flow water surface elevation was between 1 to 1.25 feet, then that would score a 2. All right, next we got the big one. Metric 10 is stream bank erosion extent and magnitude. So this is another one that has a matrix associated with it. So the first criteria you're going to look at is how much of the stream banks are considered eroding. So throughout your entire reach length, what percentage is required eroding? So if more than 75% of your stream banks are eroding, this metric scores a 1. If you have less than 10% eroding, then you're going to score in the functioning range of scoring for this metric. I will say I cannot do BHI justice in the time that we have today, but we do have Appendix E, has both guidance and photos. If you're wondering, I just said what percent of your stream banks are eroding, but Sydney, how do you define eroding? In order to be considered eroding in this methodology, we need a BHI total score of 25 or greater to be considered an eroding stream bank. And then your dominant BHI, so if your dominant BHI, that is your second criteria for scoring, is the condition, the narrative condition that describes the most length of the eroding banks. So let's say I had less than 10% of my stream banks were eroding, but though that, let's say 5% of those stream banks were described as a extreme BHI category, then I would score an 8. This is just to reiterate, these are the 2 resources that are included in Appendix E to the user manual. So we have the Fish and Wildlife Service published field methods. So BHI is part of the banks assessment that is published by Rosgin in the WARS book. But I believe Rich wrote these standards for BHI assessment and had them reviewed by Rosgin, and they were published back in 2004. And they have some great pictures that I print and take with me in the field when I am doing BHI. Also, newly available is a B-high erosion potential example. So this picture guide was put together for the Northeast Ohio Regional Sewer District, but a lot of the photos are actually from streams in Maryland. So you will find it very useful if you're just getting started with B-high. And before I show a couple pictures of B-high banks, I just want to cover. So I did say that in order to be considered eroding, you have to have 25 B-high points. So B-high goes on a scale, or it assesses 5 variables on a scale of 1 to 10. So 5 variables, 10 points is the maximum B-high score is 50. And the 5 variables are your bank height, your root depth, root density, bank angle, and surface protection. There are adjustment factors for the bank material. So if you have sand and a significant amount of sand, that's going to destabilize your bank and add points. If you have clay, clay holds stuff together. So clay, you can actually subtract points. And then there's also adjustments for stratification. So if there are eroding spaces where layers, soil layers meet, then you can add points. And I'm just going to show a couple examples. So for this bank, the measurements taken are the bank height, bank full height. We record the root depth, which in this case is not very deep. I like to call these sad lawn grasses or sad pasture grasses. They just don't do a lot to help hold a bank together. They have a sad root depth and they have a sad root density, pretty low root density. Actually, we will measure bank angle. I am really bad at estimating bank angle. So I have a clinometer app on my phone, or I have a clinometer with me in the field to measure bank angle. And then surface protection. As you can see, there's just a lot of bare dirt in this photo. So surface protection is very low. I made what I hope is a fun field form for you guys. If you are well versed in B-high, you might not like my field form and prefer to use your own, or yeah, and that's okay. But for the 2024 FBRSA, I have tried to fit on one page the scoring associated. So these across the top are the B-high scores, and the A, B, C, D, E, those are the 5 B-high variables. So the values under here are the values you would get from your 5 B-high variables, and then you'd follow it up to the score at the top. So for this bank, the study bank height was 2.8 times the bank full height, or around there. So it yielded a score of 9. The root depth was less than 0.05%, less than 5% of the bank height. So that scored a 10, and I recorded a score of 10 here. So using this matrix to record scores, I was able to determine that this bank receives a B-high total score of 45, which is definitely greater than 25 and is eroding. And the 45 does count as an extreme bank erosion hazard index. And I have a couple more examples to show real banks and the data that was measured to characterize those banks. So in this case, we have a 5.5 foot bank height compared to a 2.5 bank full height. Root depth is only 1 foot, root density is 20%, bank angle is 50%, surface protection is 30%. So taking those numbers to determine how many points it gets on the B-high scale. So I highlighted the values, and this one gets 34.5 points, which is greater than 25. So this bank is eroding, and it corresponds to a high bank erosion hazard index. And one more that is not eroding. So this one has bank height is slightly higher than your bank full height. Rooting depth is the whole way down, has a high root density because you can see we've got some saplings and some trees. We're definitely in the root fan of multiple trees on this bank. We've got a low bank angle and a high surface protection. So that bank totals to 9.5 out of the 50 which is less than 25, and this bank does not count as eroding. To tie it back together to the scoring, so you're going to walk your whole stream reach, lumping your banks together into distinct conditions. For each distinct condition you observe, and this is just based on the bank characteristics. So each distinct condition you observe, you will assess the bank and get a total score. You will use that data to determine what percent of your stream banks were eroding, and then to determine what your dominant B-high category is for those eroding banks and select a final score for your reach. And at that point, you're almost done. You can say like, gosh, all right, that took a lot of time in the field, but it was my second to last metric, and my last metric is a pretty quick one to assess. So I am almost done here. So metric 11 is anthropogenic floodplain exclusions. And the number you're going to score is the percent of the active valley bottom that is excluded, or what percent is cut off. So man has put something, either a building footprint, or you can see that this roadway in this example has cut off this floodplain from being accessed during a flow event. And so what percentage of the floodplain has been excluded? What is no longer available to the stream reach? And this picture is in the user manual. And I actually really like this picture because this roadway is really low. And the question that always gets asked is, what flow event are we thinking of for like what is, oh, you can't see my hands, but like disconnected or not included anymore? And the question isn't the flow event level. It can be a very low flow event. So it could be a pretty like a side cast berm from when they channelize the stream. Like it doesn't have to be a particularly tall levee to cut off the floodplain. The question is, what man-made structures have cut off some portion of that floodplain from flows greater than, I'd say, bankful. I think, what has cut off flows? So this roadway might actually be not that far above bankful, but it is very obviously like anthropogenic fill put into that floodplain, and it is not serving as a floodplain surface or providing floodplain functions. So this valley would be 50%, maybe greater than 50%, and receive a score of 1 for the existing condition. And I got one more example for this one. So this is, photos are courtesy of the Nature Conservancy, where there was a large project along the Pocomoke River to put breaches into levees along the Pocomoke River and open up just acres of forested floodplain and allow water to access. So for this metric, breaching levees, like just providing little cuts in it that allow water to access behind the levee, is sufficient to provide access to the floodplain. You don't have to take the levee out in its entirety. So
we have a, oh, go ahead.
Oh no, I was going to jump back to this one. So if this roadway has some cross drain culverts, then it's not disconnected anymore.
We have a question from Patrick Balzer, sorry. Do maintained utility right-of-ways count as floodplain exclusions?
If they are raised in elevation. So if there's any kind of bump or like not levee, because it doesn't have to, like usually levees are like right against the channel bank, but if there's like a bump that is like that section is higher in elevation than the rest of the floodplain, then yes.
So
if it's at grade, then no.
A tricky one could be on occasion sanitary lines, whether they added fill to the valley or not when they did that. Usually not, but sometimes I think. Or if the line's just sticking up, it's just on the surface in the floodplain. We've seen some weird stuff in the field. That might be.
But this parameter is strictly a matter of floodplain hydrologic flow. So, you have that sewer line where the vegetation has all been removed, but it's basically close to pre-existing grade. That's kind of irrelevant if it's close to pre-existing grade. Is that right?
It is, that's correct.
Okay.
But if it's sticking up and cutting your flows off, your ability to spill out in flood events, then it would count. So usually roads, buildings, sometimes if you get into the mountain regions, they're desperate for flat land to build on. So there might be a whole community there, just depending on what you're dealing with, railroads, that sort of thing.
That is the end of my slideshow, because then we have walked you through metrics 1 through 11 for assessment. We're going to go out in the field and practice and measure all of these in real life. I kind of wish I had the same slide at the end, though, that rolled it all up to overall scores. That would be redundant. I will kick it back to Nick. Are we way ahead of schedule? We're way ahead of schedule.
Yeah, thanks, Sydney. We are way ahead of schedule. That's not a bad thing. I'm going to walk through some field logistics, but do you want me to pull up a slide that has everything rolled together? Because that was my last slide of the first presentation today, and I can pull that back up.
Oh, yeah.
Cool.